Hello and welcome back to the welding and joining class. We are going to continue our topic types of arc fusion welding processes. We have covered the first 5 types of arc welding processes and we are going to now start with electro-gas welding. So electro-gas welding is basically a vertical position based welding technique which is used to weld very thick and very deep plates, okay, such as it can be used to weld railway tracks, it can be used to weld very thick plates, etc. So here the consumable electrode is used and the arc is struck between the consumable electrode and the workpiece, which is in this case this is the workpiece. A shielding gas is used sometimes, but the pressure is not applied. A major difference between electro-gas welding and its cousin electro-slag welding is that the arc in electro-gas welding is not extinguished. Instead, it remains struck throughout the welding process. So while the welding takes place, the arc can be seen and can be observed. It is used to make square groove weld. Okay, so this hole or this slot is called a groove. A groove is basically opening where we can do the welding process. So this is the groove, and it is used to make square grooves. Okay, so we are going to fill square holes. Okay, and it is used for butt and T-joint, especially in shipbuilding industry, and it can be used for the construction of storage tanks, as well as it can be used in railway tracks as well. So in electro-gas welding, we have got our electrode, which is basically direct current electrode positive, and then we have got a mold, okay, in which we have mounted our filler material and the torch, and then we've got the filler material. Here is the filler material, and the gas torch is same. Okay, this is used to create some amount of heat, and then we get a molten pool, and that molten pool fills the whole material. This is the weld metal. So in electro-gas welding, we require a copper mold, okay, and that copper mold is basically water cooled, because if there is a lot of amount of heat energy which is given to copper, then it might melt or it might basically break due to very high thermal expansion or a very high amount of heat energy given. Now the welding is done in one pass and in vertical up position. So here you can see that the weld metal is going to fill upwards in the vertical upward direction. Now the limitation of electro-gas welding is that it has got a very high heat input. So the material which I am going to weld, these are 2 plates which I am going to weld. Okay, so the surrounding part might become heat affected zone. The surrounding part might become weak in strength. Then another thing is that once this big part becomes very weak, so what I need to do is I need to carry out heat treatment process, or also called post-weld heat treatment process. So once we carry post-weld heat treatment process, it might add to some cost, it might add to some expenses. Now the application for electro-gas welding is welding very thick materials, shipbuilding, and sometimes can be used for railway tracks as well. So here is a video for you guys to go through the applications of electro-gas welding process. Next.
Hey guys, welcome to SkillLink. Up until now, the welding topics which we discussed had something in common. They were all used for welding medium to thin metal bars or sheets. But what if we want to weld thick materials, say materials with thickness over 30 mm? Such materials cannot be welded together with conventional welding procedures such as stick welding or TIG welding or even gas welding. Instead, we use a different type of welding procedure called electro-slag welding. This method uses the same basic equipment that is used in most arc welding operations: an electrode and the power source. Similar to MIG welding, the electrode is fed into the welding pool from a winding. The welding procedure is as follows. The 2 materials that are to be welded are clamped together by a molding shoe. A small gap is left between the workpieces. Below this gap, a base plate is then placed below the gap sealing it shut on both the sides with just one opening from the top. A flux material is then added into the gap. After this, the electrode is lowered into this particular gap. One end of the power terminal is connected to the electrode and another end is clamped to the base metal. An arc is initiated between the electrode material and the flux. Due to the high temperature of the arc, the flux material is melted. More flux is added into the gap till the molten slag reaches the tip of the electrode. After this, the arc is then extinguished. The main reason why the flux is added here is that it is a very bad conductor of electricity. Because of this, when the current is passed through the molten slag, joule heating occurs. This causes the electrode wire, which is in contact with the flux, to also heat up, causing it to melt and join with the flux weld pool. Since this procedure does not purely depend on arc generation, it is commonly not considered as an arc welding procedure. Instead, it is considered as a fusion welding process. The mold which is used to hold the entire weld pool is normally water-cooled. Since the density of the slag material is much lesser than the molten electrode material, it stays on top of the weld pool. This aids in continuous generation of heat as well as protection of the weld pool from oxygen and other atmospheric elements. While welding very thick materials, the holding die is moved along with the weld pool as it increases in size. Since most of the metal at the bottom would have solidified, this wouldn't be a problem. The electrode feed can also be increased by adding more than one electrode wires into the joint. Due to this specific reason, thick metals can be welded together quite easily with the electro-slag weld.
So students, next we are going to move on to flux core arc welding, FCAW. Flux core arc welding is basically a dual shield welding setup, okay, or a dual shield welding technique in which the filler material, okay, or the electrode wire has got an inner core which is called flux. So basically they have filled in the inner core of the wire, they have filled a flux inside. So what happens is that this flux is going to help in the stability of the molten metal which is formed. It is going to protect the molten metal from oxidation, contamination, and in return it is going to put, or it is going to inlay some amount of slag on the material. So basically some amount of slag cover is deposited due to the fact that we are using a flux core wire. That is why it is called flux core arc welding. So flux core arc welding is basically semi-automatic as well, because we have got this wire feeder, and this wire feeder is basically going to automatically feed the wire into our torch system, okay. Now obviously because of the fact that we have got a large amount of heat being generated, so this whole system is basically being water cooled. So those machines, FCAW machines which are more modern, are now water cooled because they want to keep the electrode area as normal to the ambient condition as possible. So the reason why it is called dual shielding gas or dual shield welding setup is because this is flux is basically the number one shielding, and number two shielding is due to the gas that we can produce or we basically use or supply. So flux core arc welding can be of two types: one in which the shielding gas is not used, only the flux core is used, and one in which both of them are used. That is why it is called dual gas dual shield welding setup. So the only difference is that automatically the wire is fed into the machine, and manually the torch is used by the welder. So the welder is going to manually use the torch to create a weld seam. So that is why it is semi-automatic welding setup. So flux core arc welding basically has different advantages and different disadvantages. The advantages are that flux core arc welding provides is more preferable to metal inert gas, okay, MIG or MAG welding, okay. Why it is preferred? Because we have got an additional shielding which is available. Now MAG cannot weld very thick material. However, by using flux core arc welding, because we are improving the stability of the system, so we can further increase the thickness of our material in comparison to MAG metal inert gas welding. Now the built-in shielding provided by the filler wire, so the filler wire that we have, and inside we have got a built-in shielding flux. Okay, this basically can endure the wind effect also. So during welding, what happens is that the wind can also come and it can basically create destabilize the arc. So in order to basically protect the arc, we have got the flux coming in also. So filler wire can endure strong breeze, and if used without an external shielding gas, flux core arc welding is more portable and more convenient. The welding process also provides more flexibility with alloy compositions than metal inert gas welding, and it offers high deposition rates also. So you can see that the productivity increases. Okay, it is less bulky, it has more advantages than SMAW and GMAW because we are using a continuously fed flux filler wire. Yeah, one of the disadvantages is that because of the flux, smoke or gas is produced, and slag is also produced onto the weld, which has to be later on removed during the welding process. So flux core arc welding can be done in all the positions. Okay, the flat head position, the up and the down position. Okay, the overhead position, it can be done from all the positions because of its flexibility and because of its durability and portability. So the welding operator, okay, he or she does require less amount of skills. So the skills required are lesser when compared to SMMW or GMAW. Now there are a few disadvantages of the process compared to other welding techniques, such as include producing noxious, okay, the gas is noxious oxides. Okay, so very noxious smoke is produced, which is more dangerous and detrimental for the environment. That is why flux core arc welding produces more smoke. It produces more smoke than MIG or SMAW. Flux core arc welding electrodes are expensive, okay, because we have got an additional manufacturing process involved to put the flux within the core of the filler material. So that is why it can be sometimes more expensive. The filler wire has to be chosen very correctly, okay, to ensure that the required mechanical properties are also obtained. Another disadvantage is slag formation for flux core arc welding. However, one of the best advantages is that it can produce a weld for very thicker plates as compared to SMAW, G and AW. So a very good amount of range of alloys, aluminum, different types of steels can be basically welded with the help of plain carbon steel, okay, stainless steel, duplex steel can be used for with the help of this FCAW process. So this was all about flux core arc welding processes. Now you guys will go through a video and you will see further details of the process.
This is an illustration of the process and components involved. We have our torch, we have our electrode, which in this case is a hollow wire filled with flux. We have our arc, which is creating the heat to melt all of our metals together. Then we have the smoke that's produced from the flux when it burns, and that's creating the shield around our weld puddle. Now the little globs that you see flying in slow motion, that's actually the filler material that's coming from the torch, getting transferred into the weld puddle, thus creating our weld. And it's as simple as that. So I'm just gonna make a quick weld right here. Now I'm going to slow that way down to give you a nice visual of exactly what's going on during that process.
So now that we have gone through different types of arc welding processes, let's take a look at some of the comparison between some of these processes. So as you know that all of these processes are very unique, and some of them have different process. Some are automatic, some are semi-automatic, and some are manual. So the first thing which a manufacturer see or observe is the cost of the equipment basically. So if you can use the lowest cost, then perhaps it is feasible for your product that you are going to manufacture. So the first thing that you're going to look is whether the cost is reasonable for you to manufacture the product. So in this case, if you see that shielded metal arc welding or SMAW or manual metal arc welding is basically the most reasonable one, and it can basically carry out welding in all positions. Next we look into some of the advantages. Okay, let's say for specialized process you're looking for very high deposition rate, then you will opt for submerged arc welding. However, provided that the welding position is only flat and horizontal, you cannot go top to bottom or bottom to top, uphill or downhill welding. So next we move on to gas tungsten arc welding. So yes, it has the advantage of carrying out all the different types of metals can be welded. However, the typical cost of the equipment is quite high, and the amount of distortion produced is also quite high. So you need to look into the fact that how much is the distortion which is produced by these processes. For instance, electron beam and laser beam welding have the tendency to produce very high distortion. So you have to be very careful in these type of regard. Next, also you have to look at whether you have got the additional skills. The workers are qualified, and the operators or worker depends on whether it is manual or automatic are qualified or not. So these are something that we have to look into as well when choosing a suitable process. So depending on the application, the cost, the amount of quality that is required, we will choose our welding setup. So for instance, if I ask you what is the difference between shielded metal arc welding and gas tungsten arc welding, then you can perhaps go back and see the difference in terms of operation advantage, welding position, current type, etc. So for instance, here are some of the answers. So for electrode, shielded metal arc welding uses coated, whereas gas tungsten arc welding uses non-consumable tungsten electrode. Then the filler is required for gas tungsten. Shielded metal arc welding has electrode which acts as a filler. Then we talk about shielding gas. Then perhaps for SMW no shielding gas is required. For GTAW argon gas is required. So these are some of the difference that one should be able to make when choosing the right type and technique for welding. So now we move on to fusion welding, another type which is American Welding Society AWS unique processes. So if you go back to the lecture number 1, then you will see that there are some unique processes which are highlighted by AWS. This is because they are very high energy density. The amount of heat produced within a very small area is very large. So that heat input is basically very large. So these are categorized as high energy density processes. So now we are going to look into what are some of the high energy density processes. So now that we have gone through fusion arc welding processes, now we move on to fusion AWS unique processes. So the number 1 is electron beam welding. Electron beam welding is basically a fusion welding process in which the electrons are generated by an electron gun. So here is an electron gun, and the electrons are accelerated at a very high speed, and these high speed electrons are accelerated using electrical field which is generated with the help of voltage difference between cathode and anode. This high speed and high stream of electrons are highly focused. So basically we have got a focusing coil, and using this focusing coils, the diverged electrons are basically converged. Okay, and then these focusing coils are basically using magnetic field, and then the electron focus are converged. So the beam of electrons create a kinetic energy. So they have a very high kinetic energy as they are moving from, and as they are being focused, and the kinetic energy impacts with the workpiece, so it is going to impact the workpiece, causing them to melt and bond together. So the melting is going to occur, and then these two type of material will bond together. So electron beam welding, as you can see, is carried out under a vacuum because for generation of electrons a vacuum is required. Due to it being a vacuum process, very high voltage are required, and this welding method is heavily automated and computer controlled. As a result, specialized fixtures and CNC tables, so the table is made of CNC, computerized numeric control tables are used to move the workpiece within the welding chamber. So electron beam have various disadvantage because it is very precise. Okay, it has highly repeatable process, and because of the fact that it is highly automated, then this welding technology creates strong and very strong with very high tensile strength and pure joints, because there is no contamination, because it is carried out under vacuum, so the oxygen is not present. So when the oxygen is not present, then it cannot create porosity or pores or different types of cracks or welding defects. So electron beam welding offers precise welding penetration, and the depth of penetration and the preciseness of the depth of penetration can be equal to 0.0001 inch. So if you are working for aerospace industries and you want extreme precision, then electron beam welding is very good. Another advantage is that electron beam focus very high amount of heat on a very small region. So the spot of the electron is very small, and the amount of heat is very high. So it causes rigorous melting, and the amount of penetration depth which is achieved is also very high. So usually for gas tungsten or shielded metal arc welding, the weld pool looks like this. But however, for electron beam, when the electron strikes on a very small narrow region, then the weld exactly looks like a straight line. So this is one of the advantage of electron beam welding, that there are no impurities, there are no oxides, no nitrites in the weld pool, and it is a very highly automated and controllable process. One of the disadvantage of electron beam welding is that the electron beam welding technology is very expensive. So the cost of electron beam welding setup is very high, and it requires a lot of maintenance also. So these are two things which are very which can be a disadvantage for you, but however for specific applications these are advantages. So here is basically a diagram of an electron beam welding, and here is the penetration depths of TIG welding and electron beam welding, and here you can see that the penetration depth, okay, this distance from the top surface to the maximum weld zone is called penetration depth, PT, and for you can see that for PT penetration depth for TIG is quite low, whereas for electron beam welding the penetration depth is very high, and it can do the welding at 40 centimeter per minute. You can see that the base material is only 6 millimeter thick, so the thickness of the material is only 6 millimeter, and here it is around 13.5 centimeter. So you can do electron beam welding for very thick materials as well. So this was all about electron beam welding, and you will now go through a electron beam welding video.
Yeah.
The electron beam welding machine consists of two main sections, electronics and physical section. The physical section consists of the vacuum working chamber with the pumping system, the manipulator and the electron gun as the electron beam source. One part of the electronic section is a high voltage power supply to accelerate the electrons. The welded parts are placed in the working chamber and the inner space is evacuated. The electron beam is focused onto the surface of the welded workpiece and the weld is formed by mutual movement. welding is usually performed without any additional material. The combination of the deflection system and the computer can be used to display the workpiece in the electron microscope mode, to weld along complex paths, or to create seemingly multiple beams for multi-pool welding. The deflection system is also used for engraving and local heat treatment of the surface layer, or in 3D printing using selective melting. A typical feature of electron beam welding is so-called deep penetration effect. Power density of the electron beam reaches such values that the beam penetrates the material very rapidly. Thanks to this, the weld acquires its typical knife-like shape, even for very deep welds.
So students, now we move on to laser beam welding, LBW. Laser welding or laser beam welding is a process to join together metals or thermoplastics using a laser beam, and that laser beam is an acronym LASER. Laser means light amplification by stimulated emission of radiation. So the laser beam is also works similar to electron beam welding, where the laser or the photons are basically concentrated with the help of a lens, and they are concentrated to a very small region which produces a very high amount of heat energy density. So basically, if you have this area and you have a very large amount of heat, then the heat flux, or let's say heat per unit area, okay, or flux, is very high. Although laser beam welding flux or heat flux is lower than electron beam welding, but still it is very high, and it is quite higher than other types of welding processes. Laser welding can be carried out at very high speed, so I can move the workpiece or I can move the laser head at a very high speed, depending on which of the laser head or the workpiece is automated. Thicker materials can also be welded, and I can get a very deep and very narrow welded zones. So the laser basically operates in different modes, and laser welding is usually accomplished with a very high power or very high energy density. So the deeper penetration, small, thin, large, thick products, all can be welded. Filler material can be used or cannot be used, it is up to us. So it is a hybrid process. Now laser welding is not carried out in vacuum usually. That is why some oxidation or some contaminants can enter the weld pool. So laser welding has got various advantages, such as we can use it for very high production rates. Okay, we can use it for welding thick and bulky what we call parts. We can use or combine different lasers to welding simultaneously as well. So it is a very highly flexible process. We can mount this whole laser welding head on a robotic arm, so this can be used also for welding all the automotive sheet metal. So the car industry uses laser robotic arms to weld the car body as well. So laser welding has one of the highest applications in all the different types of welding techniques. So here is basically a construction of carbon dioxide laser and Nd:YAG laser. So here are some of the welding which are carried out in our lab, JWL lab in block A4, joining welding and laser processing lab. This is a 200 kilowatt laser. The laser is emitted from the laser head, and there is a lens, and that lens is used to focus the laser beam onto the sample. This is a nozzle for putting argon gas so that we can prevent oxidation or contamination. So it is always required to have a good shielding gas as well for laser welding setup. In our case, we have got belt conveyors. Okay, so these belt conveyors are used to mount, and these belt conveyors are used to move the samples. These belt conveyors are basically controlled by CNC G and M codes, whereas the laser head position is fixed on the structure of our machine. So you guys can go through the video. Later on. So when we talk about different energy densities of various welding techniques, then here you can see that shielded metal arc welding has the one of the smallest penetration depth. Okay, so it is quite less. However, as we move on to plasma arc welding, we know that the arc is constricted and it comes out from a nozzle or from an orifice, which is basically also assisted by an orifice gas. So the plasma arc welding produces even larger depth. Then laser beam welding is controlled by photons, and those photons basically penetrate deeper. However, more deeper than photons penetrate the electrons, and this is the case of electron beam welding. So electron beam welding has the highest amount of energy density and has the highest amount of penetration depth. Here are some of the energy densities of various welding processes. So next we move on to fusion state. Liquid state energy is chemical and it is also a part of AWS unique process. So thermit welding is basically the process that we are going to discuss. So the process of thermal or thermit welding is basically due to the fact that we have got a chemical, okay, and that chemical is made of, it can be made of different things such as iron oxide, or it can be made of aluminum powder and iron oxide, and they are mixed at a ratio of 1:3 by weight. So I'm going to put my powders here, and next what we do is we preheat this mixture using oxyacetylene fuel. Okay, so using a burner I'm going to heat this at 1300 degree centigrade. So when we heat this at 1300 degree centigrade, then a reaction takes place, and 3000 degrees of melted material is basically 3000 degrees is achieved. So thermit welding is basically a chemical welding process in which an exothermic reaction, because I am heating this and there is a reaction between aluminum and alumina oxide powder. So thermit welding is a chemical welding process in which an exothermic chemical reaction is used to supply essential heat energy. That reaction involves burning of the thermit. So this is called thermit, the mixture of iron oxide and aluminum powder in ratio 1:3. So the temperature attained is 3000 degree centigrade. The aluminum oxide floats on the top of the molten metal in the form of slag, and the pure iron steel settles below because of the very large difference in densities. So the steps involved in the thermit welding are that first the two pieces of metal which I want to join are properly cleaned and the edges are prepared. Then a wax is poured into the joint so that the wax pattern is formed where the weld is to be obtained. Next, the molding box is, okay, you have got a molding box is kept around the joint, and refractory sand is packed carefully around the wax pattern as shown in the figure. At the bottom opening is a runoff, so we got a runoff of the molten wax. The wax is melted through its opening, which is also used to preheat the joint. This makes it ready for welding. The thermit is mixed in a crucible, so you've got a crucible which is made of refractory material that can withstand very high amount of heat, and then we have got an igniter or a torch which is used to ignite the whole system. The reaction takes place for about 30 seconds, so it will take about 30 seconds, and a very highly superheat molten iron is allowed to flow. So iron is allowed to flow as well, and into the prepared mold cavity. So the prepared mold cavity will be basically filled with all the iron. The superheated molten material fuses the parent material and solidifies into the strong homogeneous weld. The weld is now allowed to slowly cool. So here is an example of these two parts. These are two different rail, and then I have got this mold into which I put the iron, and then this joint has formed due to thermit welding. So thermit welding is specifically used for welding of rail cars and railroad systems. So the advantage is that I can do this, or I can put this chemical on site, so I don't need to carry very high amount of power supply, etc. I can just do it on site, okay, and it has got very good casting quality. So it is basically a type of casting process basically. So here is an example of thermit welding. After this, this is basically the end of fusion welding, and now we are going to move on to the second part of our fusion welding process, which will be resistance welding. Thank you for listening to the lecture.